by a box. And the box just shows you the location of those electrons, one spin up and one spin down. Now this is going to perhaps make a little bit more sense as we go along from left to right. So once again, let's start over here. So here is your S subshell. Your S subshell can contain 2 electrons. And so if we go to put the electrons in there, the first atom is potassium, which is only going to have 1 electron spin up, which is why the potassium is a little bit of magnetism here for that guy. He is slightly paramagnetic. But now if we go to make this guy into calcium, now we have to put in the second electron, but the second electron in any box must be spin down. Those two now cancel each other out, which is why this guy again is diamagnetic. All right, now let's go to the next subshell, which is the D subshell, the 3D subshell for these guys. Now take a look in the 3D subshell. We're going to start with scandium and go all the way over here to zinc. And in that subshell, there are 10 electrons. And if there are 10 electrons, and we know that you can fit 2 electrons in a box, then how many orbital boxes are you going to need for the Ds? Well, that's pretty simple arithmetic. 10 electrons, 2 electrons per box, you're going to need 5 boxes here. All right, so there they are, 1, 2, 3, 4, 5 boxes. Now let's go ahead and see what the data tells us about how to fit those electrons into the boxes. So our first one here is going to be scandium. That's pretty obvious. Well, for scandium, all we're going to do is pick a box. It doesn't matter what order you do. I just tend to go left to right. And it doesn't matter whether you start up or down. Typically, you just start up. That's how you typically do it. You don't have to, but that's the way you'll probably see it. And so there's scandium. So scandium here has 1 electron in the D subshell, and that electron is here in that orbital, and it is unpaired. It has nothing canceling it out, which is why we see that scandium is a little bit slightly paramagnetic. Now, how are we going to put the next electron in there for titanium? Well, we've got some options. Remember, that is not allowed. That's no good because you can't have 2 electrons in the same box doing the same thing. So, if that's not the case, we could do that. So put 1 up and 1 down like we did before. But does the data back that up? Titanium here is still paramagnetic, and not only is it paramagnetic, it's even more paramagnetic than the scandium was. And so if we were to put it like this, well, that wouldn't go with the data because now we've got 1 up and 1 down. And if we've got 1 up and 1 down, they should cancel each other out. And so if that was true, then what we should see for titanium is a 0 response to a magnetic field, or 0 or diamagnetism, 0 paramagnetism. And that's not what we see. We see even more paramagnetism. So if that's the case, then what is our next choice? Well, we have other boxes available. Why not just put the electron in that box? And so if that's the case, why don't we put it in the next box over and put it also spin up? Well, now we've got 2 electrons that are next to each other that are spinning in a similar direction. That is going to be constructive interference, and so that's going to make even more magnetism, which is what we see. Does this trend continue? Well, our next one up is vanadium. And what do we see for vanadium? We see even more response to the magnetic field. So what are we going to do? Well, we've got more boxes with nothing in them. Why don't we go ahead and put in the next electron that is going to be spinning up? Now we have 3 unpaired electrons that are all half-filled spinning in the same direction. That is going to make even more magnetism, which is what the data shows. And if we continue this trend, we can go from chromium and, that should be manganese. I don't know what happened there, Mn. And manganese should be next. So here's chromium with 1 more, and here's manganese like so. So that gets us all the way through to halfway across the subshell. So there's halfway. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We are now halfway through. And as we are halfway through, we have 5 boxes that are now half filled, spinning the same direction, which is why we see a steady increase, a little bit more, and now lots. We see a steady increase across the subshell. But now that we're halfway, we have to put in electron number 6. But there's no other unfilled boxes to put them. So if that's the case, then where do we have to put the electron? Well, we have to start somewhere, but now we have to put the electron going down, because you can't have all spin up going in the same box, and you can't have all spin down going in the same box. You have to have them in opposite directions. So our next electron is going to go there, spin down, which now makes this one diamagnetic and these 4 paramagnetic, which means that there's going to be only 4 unpaired electrons, so iron should be a little bit less than the one before it, and oh, look at that, that's what we see. Still magnetic, still lots, but not nearly as good as the one before it. So that's where iron is. And if we continue then this trend all the way through, the next one is going to be cobalt. I have to put another electron in, spin down. The next one is nickel. I have to put another electron in, spin down. And then copper, I have to put another electron in, spin down. And finally zinc. And now by the time we get to zinc, all of the orbital boxes are completely filled with 1 up and 1 down. There is no unpaired electrons. And if there are no unpaired electrons, it is diamagnetic, because all of them cancel out. So that's 1 up, 1 down, they cancel out. 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 And sure enough, that's what we see for zinc over here. 0 response to a magnetic field. If we were to do now the same thing for the p subshell, it would be of even higher, but the p subshell only has 6 elements. 1, 2, 3, 4, 5, 6. So how many boxes would I need to draw? Well, 6 electrons, not 6 subshells, 6 elements in the subshell. So if there are 6 elements, 6 electrons, that means I'm going to need 3 boxes to fit those. So I'll draw 3 boxes. And now, here is gallium. I'll put in 1 going up. Here is germanium. I'll put in another going up. Here is arsenic. I'll put in another going up. And now selenium, bromine, and krypton will go down, down, and down, which is why you see the magnetism start slight, go a little higher, go a little higher. But now that we're halfway through, you would look like this. You're here at arsenic and you're halfway in. And now you're going to have to go with selenium, bromine, and krypton, which is why you're going to go down, down, and down, and now you're completely filled. And when you're completely filled, you are diamagnetic, which is why krypton here looks like that. So all of this goes together to be what is called Hund's rule. And Hund's rule says that the most stable arrangement of electrons in a subshell is when degenerate orbitals are half-filled spinning the same direction, or when they are totally filled. And degenerate is just a term that means duplicate subshell orbitals. So basically what it says is you're going to take a subshell and you're going to half-fill everything first in one direction, and then you are going to refill them in the opposite direction. And when it's half-filled, it's super stable, and when it's totally filled, it's super stable, according to what's called Hund's rule. So let's take a look now again at how this goes. Potassium, our first one. Only 1 valence electron. All you're going to see is that. Calcium, 2 valence electrons. 1 up and then 1 down. And now scandium, 3 valence electrons. We're going to go 1 up, 1 down, and then 1 up. Titanium, 1 up, is going to be 1 up, 1 down, and then 1 up, 1 up. And if you continue this all the way across, then vanadium is going to be one up, one down, up, up, up. Chromium, up, 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 and then up. Manganese, up, 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 and up. And by the time you get to iron, now, because iron is halfway through, here is your subshell. There's the D. We're 1, 2, 3, 4, 5 in. Now iron is going to be up, down, and then 1, 2, 3, 4, 5, and then 6 in. Cobalt, 1, 2, 3, 4, 5, and then 6 and 7. Nickel with its S, and then 1, 2, 3, 4, 5, 6, and 7. Copper, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Zinc, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I forget one for nickel? I think I forgot one for nickel. There we go. I forgot one for nickel. Thought that seemed a little off. By the time we get to gallium now, we've got 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now 1 over here in the P subshell. Germanium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now 2 in this. Arsenic, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, and 3, which, by the way, is halfway through the P subshell. Selenium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now 1, 2, 3, and then 4. We have to go back down in the other direction that's there. That was a bad arrow. Bromine. So you can see how I'm doing each of these. We are half filling each of them and then refilling them. Krypton is half filled and then now is totally filled. So you can see the progression of the filling of those orbitals as they go across. Hund's rule says we go halfway and then go back and fill it in the opposite direction. Or if we were to look at it in this way now, instead of looking at it as just the subshells, we are now looking at the subshells. So at the first energy level, we're going to do that, and then we're going to do that. And then our next one, we're going to do up, and then we're going to do down. And now at the 2p, we have 3 boxes. Again, these things are just the boxes. That's all they are. So we're going to go up, up, and now down, down, and down. Sometimes they just draw lines instead of the boxes. It's the same thing. S's, we go up, and then we go down. P, we go up, and then down, down, and then down. And now here we are, the 4S. We're going to go up and then down. And this is what we just did. We're going to go up, and now down, 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 and down. And you get the idea, I hope, by this point. So, these are the types of questions that you will see about these things because you can make some logical leaps of